This video provides an introduction to the paired t-test with an example using SPSS. The paired t-test is used to test hypotheses about related means. Examples include pre-test and post-test scores, measurements taken from two quadrants of the same mouth, matched pairs where scores are considered to have come from the same source, and other situations in which the same subjects have scores under two different experimental conditions, such as a crossover design. The paired t-test controls for individual differences because the same subject is in both treatment conditions. The test focuses on differences between the two scores. It is similar to the one-sample t-test, and the degrees of freedom is also n-1. The first assumption is random or fair sampling. The second is paired samples. Each subject provides a pair of scores, from which we calculate a difference score. Difference scores are assumed to be independent of one another. This means, for example, that we do not collect more than one pre- and post-score from each subject. The normality assumption presumes strength of measurement, that is, quantitative data. When the sample size is large, the sampling distribution will be approximately normal according to the central limit theorem. Suppose we're interested in the effectiveness of aspirin in reducing temperature. 30 otherwise healthy adults suffering from flu symptoms report to a health clinic and have their temperature taken immediately before and 1 hour after taking 250 milligrams of aspirin. Aspirin is an antipyretic. We expect temperature to decrease, so this is a one-tailed test. Our sample consists of adults with flu symptoms who walk into a health clinic, so we would treat this as a sample of convenience. This affects our ability to generalize. For example, we wouldn't make inferences to those who are too sick to visit a clinic, or those who would never go to see a doctor. Each subject has a temperature value before and after taking aspirin, so the second assumption is met. No one has more than one difference score, and knowing one individual's temperature change should tell us nothing about another's, so the independent differences assumption has been met. The sample is large, so the sampling distribution of differences will be approximately normal. The null hypothesis is that the population means are equal, or that the difference is zero. The research hypothesis is that the mean temperature before aspirin is higher than mean temperature 1 hour after taking aspirin, or that the difference is greater than zero. Each subject has a before and after measurement, so our data might look like this. The paired t-test formula is identical to that for the one-sample t-test, except that the variable is a difference score. Now let's look at the results from SPSS. The first table shows descriptive statistics for the two variables that make up the difference score, and we can see that the mean temperature was higher before than after aspirin. The p-value for the t-test is very small, but it's not zero. This was a one-tailed test, so we divide it in half to get the actual p-value. We would say that there was a significant decrease in mean temperature after taking aspirin. We can estimate the size of the effect using a one-tailed confidence interval. We get d bar and the standard error from the t-test results, and find the critical value of the test statistic from a table. Plugging these numbers in, we get a lower bound of 1.11, and would say that we are 95% confident that the mean temperature reduction is at least 1.11 degrees Fahrenheit. A difference of 1 degree may not seem like much, but it is the equivalent of 1.25 standard deviations, which is a large effect size. The next video presents an example of a paired t-test with unmet assumptions.